All right, so we're talking about exponential growth and decay. So we've kind of seen these equations before, but we've never graphed them like this or looked at them in this way. So the parent function for exponential growth and decay is the same. So you have f of x equals b to the x. When it's growth, you're going to look at this base to your exponent. So with exponential functions, x is going to be in the exponent. If that number that's the base is bigger than 1, then it's going to be a growth. So if I look at the equation of that from left to right, it would start and then go up. All right, so it's growing. So if I had, say, 3 to the x, 3 is bigger than 1, so that makes this a growth. If there's a number out front, say a 2, I don't care about the 2. I only care about the base of the exponent. So with decay, that number would be between 0 and 1. Not a negative number, but between 0 and 1. The negative just means it's going to flip the other direction. And then from left to right, my equation would be going down. So if you're trying to decide if it's growth or decay, you're going to look at the base of your exponent. The base of this exponent is 1.5. That's bigger than 1, so that makes this a growth. Whereas on number 2, 0.25 is the base of your exponent. That is in between 0 and 1, so that makes this a decay. If you prefer a fraction, you can always go to your calculator, put in the decimal that you want to change to a fraction, press the math button, and choose option 1. Press enter. It'll tell you that it's 1/4. So if that's more helpful, you can do that. So let's look at some examples where we're going to graph them. I'm actually only going to graph number 3 because we've graphed quite a few things, so we'll leave it at that. So I'm going to look at this and tell if it's growth or decay. So I look at the base. The base of my exponent is 2. That is bigger than 1, so this is a growth. If you look at number 4, the base of the exponent is 1/2, so that means that this is a decay because 1/2 is in between 0 and 1. So if I graph number 3 here, I'm going to go to the y equals, make sure you've taken everything out, put that equation in, and then graph it. We've already decided that this is a growth. And I'm zoomed a little far out, so I'm going to zoom back in. So zoom 6. So if you look, it looks like it's touching 0 right here, but it's really not. It's just really, really close, and that blue line is thick, so it kind of looks like it's covering it up. All right, so I want to graph this on paper, so I'm going to press the trace button. It's going to start me at this y-intercept right here. So I know I have a point at 0, 1. So I'm going to put a dot there at 0, 1. And then we need to put some stuff on the left-hand side, so just arrow to the left. So you can kind of eyeball this. So when I'm at -1, I'm almost at 1/2. So I'm going to graph that. Almost -1 up to almost 1/2. All right. And then let's put another one over here. So if we go all the way over till when x is about -2, looks like I'm going to be almost to 1/4. So I'll plot that point. And then I need some points on this side, and you need enough that you don't have to have a bad-looking graph. So enough to where you can follow the shapes. I'm going to go when x is about 1, and I'm a little bit past 2. So 1, 1, 2, a little bit up. All right, and then we'll go to when x is about 2. I'm about a little past 4 1/4. And I think we can do one more. All right, so when x is 3, I'm a little past 8. And I don't think I can fit any more on here. So you should fit as many as your graph will allow. So if I go when x is 4, I'm off the graph. Now, some of your graphs are on homework sometimes will start at the bottom and go all the way up to, say, 30. If that's the case, then you would need to keep going. The other option for this is you could go to your table, and if you need to go to the Setup menu, second window, you can choose Auto, or you can choose that you want to put your own x values in, and you could do it this way, kind of making a table of values. So 2, 4, 3, 8, 4, 16. So it's rounding these for you. You can even scroll up and down, okay, to get some values to plug in. Some people like that better. I think it's a pretty good idea. Maybe a little bit easier. All right, and so once you have that, you're not going to cross 0. So you'll connect your dots. Make sure you put arrows on the end to show that it's going. So you would do the same thing for anything that you were graphing. All right, so exponential functions are used a lot in growth and decay of like valuables, or when you're talking about investing, savings accounts, anything like where you would do a loan, okay? So decay would be when the value is going down. Growth would be if the value is going up. So sometimes you need to think a little bit about your problem as to whether you'd have growth or decay. If I talk about buying a car, that's going to depreciate in value over the years, okay? So number 5 is talking about the value of a car in thousands of dollars. That's important, thousands of dollars. And it can be approximated by this model where T is the number of years since the car is new. Okay, so this number that's on the outside of the parentheses, that's the initial amount. That's the amount you start with. So in this problem, that would be 25,000 because I'm talking about the value of my car. Okay, R is your rate written as a decimal. All right, so if I'm talking about 5%, I would just take the 5 and I would move the decimal 2 spots to the left and fill that blank in with a 0. So 5% is the same thing as 0.05. Okay? And then T represents your time. Okay? So it says tell whether the model represents exponential growth or decay. So I'm going to look right here, the base of my exponent, which is 0.85. That is smaller than 1, so that makes this a decay. Okay. Part B, identify the annual percent increase or decrease in the value of the car. Well, I know that it decreased in value, right? And this number right here, since I'm talking about decay, represents the 1 minus whatever the rate was. So if I took that, 1 minus my rate, that's equal to 0.85, and if I were to solve for R, or just think about it, if I have $1 and I take away something and I have 85 cents left, that would be 0.15, right? I took 15 cents away. So that would be 15%. So if I want the percent, I would just go backwards 2 spaces and get my percentage. So then it wants us to estimate the value when the car will be $8,000. So that's where I would recommend going to the calculator. You're going to put in this equation. So if y equals 25 times 0.85 raised to the x. Now, x is the t, right, representing time. That's what we're looking for. And we're looking for a value of $8,000. So you have a couple of ways of doing this. One would go to your table. Okay, so after 1 year, I'm down to 21,000. 2 years, 18,000, so on and so forth. So I'm looking for when I have a value of 8,000. So in year 6, I'm still worth over 9,000. In year 7, I'm worth over 8,000. And in year 8, I've dropped down to $6,800. So right here in year 7 is when I reach a value of 8, so 7 years. And remember, these are in thousands. That's important to think about. All right, in 2000, the world population was about $6.09 billion. During the next 13 years, the world population increased by about 1.18% each year. Write an exponential model giving the population y in billions t years after 2000, and then we'll estimate the world population in 2005. So first, let's start with writing the exponential model. I know that I am increasing, so I'm going to be using the model of a times 1 plus r raised to the t. Okay, so remember, a is your initial amount. So I know I've got y equals 6.09 times 1 plus my rate, but not as a percentage, as a decimal. So I need to take that 1.18 and move the decimal 2 places to the left. So that would give me 0.0118 to the t. All right, so if I actually simplify that a little bit, that would give me 6.09 times 1.0118 to the t. So there's the equation. Then it says estimate the world population in 2005. Well, remember, t represents the years after 2000, so that means t would have to be 5 because 2005 is 5 years since 2000. So I'm literally just going to take 5 and plug it in for t. So I have y equals 6.09 times 1.0118 to the 5th power, which is going to give you about 6.5, and we are in billions. So it says estimate the year when the population was 7 billion. So go grab your calculator, put in your equation, which was 6.09 times 1.0118 to the x, which is representing the t. So we are looking for a y value of 7. We want to figure out what year that would be. So I'm going to go to my table. All right. So when I get up to 9 years after 2000, I'm still at 6.7. All right, so in year 11, I'm at 6.9. Year 12, I'm at 7. So I've crossed over in year 12. So 12 years after 2000 would be about 2012. All right, number 7, the amount y in grams of the radioactive isotope chromium-51 remaining after t days is y equals a times 0.5 raised to the t over 28, where a is the initial amount in grams. What percent of the chromium decays each day? So first things first, there's something up here with this t value, and it shouldn't be that way. So I'm actually going to kind of split this off. So if I thought of this as, if I move the t out to the side, this would be 1 over 28. So this is actually 0.5 to the 1 over 28 raised to the t. Because if you think about your exponent properties here, if I raise something to another exponent, then those get multiplied together. So I can kind of break them apart to serve my own difference. All you want up here is just the variable. Okay, so if I actually plug in 0.5 to the 1 over 28, that's going to give me 0.9755. I'm going to round 4 places down, so 0.9755 raised to the t power. Now I can look at that number and say, okay, this is definitely a decay, which they pretty much already told me that, correct? So I'm going to do the same thing that I did in the last one. I want to figure out what that 1 minus r value is. So if I took 1 and I subtracted a rate and I ended up with 0.9755, what was the rate that I had in here? Well, just solve for r, okay? It's a little harder when you have 4 decimals. So you have negative r equals 0.9755. If I subtract 1, that gives me 0.0245, a negative 0.0. And then I'll divide by the negative 1, which gives me 0.0245. So I'm going to replace that. I have a times 1 minus 0.0245 to the t. This number right here represents my rate. All right, so if I want it as a percentage, I'm going to take it and move the decimal 2 places to the right. So this would be 2.45%, and that's what they asked. So every day, 2.45% of it decays. All right, so when you take out a loan, they compound your interest. Sometimes it's compounded quarterly, which is 4 times a year. Sometimes it's compounded monthly, which would be 12 times a year. Sometimes it's compounded continuously. Sometimes it's compounded once a year. Okay, so this is the equation that they use for that. So A is going to represent your amount in the end. P represents the principal, which is the amount you start with. R is still your rate. N is how many times per year you're compounded. And then T is how many years that you're talking about this. So if I compounded quarterly for 4 years, then the 4 would be how many times I compound. Quarterly is 4 times a year, and then times the year. So this is if I deposit $9,000, so that would be the amount I start with, my principal, in an account that pays 2.46% annual interest. So that's my rate, and I want it as a decimal. So I'm going to move that 2 spots to the left, which would be 0.0246. Find the balance after 3 years, so that would be my T, when the interest is compounded quarterly. Quarterly means 4 times a year, so my N will be 4. So it's giving you everything you need. You're finding your balance in the end, which would be the A. So you're literally going to plug in everything. So A equals 9,000 times 1 plus your rate, which is 0.0246, all over how many times you're compounding, which is 4 times a year, raised to the how many times you're compounding times how many years. Okay? And then you just plug that into your calculator just as it looks. So I have 9,000 times 1 plus, get a fraction, and you have 0.0246 over 4 raised to the 4 times 3, or if you want, you can go ahead and put 12 up there. And you get 9,687 and then 13 cents. So you're only rounding 2 because we only have 2 decimals per cents. So you have $9,687.13. So in 3 years, he made $687.13, which isn't too shabby. All right, number 9. You deposit $8,600 in an account that pays 1.3% annual interest. Find the balance after 4 years when the interest is compounded quarterly. This is exactly the same. This is my principal. My rate, if I move it 2 places to the left, would be 0.0132. T, years, so that would be 4 years, and quarterly would be 4 times a year. So I have my balance is equal to my principal, 8,600, times 1 plus my rate, which is 0.0132, all over how many times I'm compounding, raised to how many times I'm compounding times how many years. So if you plug that in, you're going to get 9,065.49. So in 4 years, I made about $465. Okay, last one. So I'm finding the amount in account earning compound interest after 6 years when the principal is $3,500. The rate is 2.29% and is compounded monthly. So after 6 years, that would be my time. My principal is $3,500. My rate is 2.29%. So as a decimal, if I move that 2 places to the left, that'd be 0.0229. And compounded monthly, within a year, there are 12 months. So that would be 12 for my N. So I get 3,500 times 1 plus 0.0229 over 12 raised to the, how many times compounding, or how often I'm compounding times how many years, which is going to give you $4,014.98. It's really not that much to make after 6 years.